Okay, so here's our last section of the semester, 16.4. We're going to talk about what we call improper integrals. So in the last couple of sections, we've been talking about indefinite integrals. That's the antiderivative. We've talked about definite integrals. Remember, that's the area underneath the curve from A to B. And now we're going to talk about what we call improper integrals, where we're going to integrate, but there is no starting point or ending point. One of those limits of integration are going to be to infinity. We're going to keep going and going and going. Before we start, let me kind of guide you and lead you into what we're going to talk about today. Will you look at the three problems up here that I have for you? The first one is our definite integral. I'm asking you to integrate x to the negative 3/2 from 1 to 5. We've done this in the past sections, and so it looks a little bit weird to me, so I'm going to rewrite that negative 3/2 into a fraction that I'm a little more comfortable with. I'm then going to use my integration rules. I'm going to add 1 to the exponent. And so be careful when you add 1 to the exponent and divide by that new exponent. I ended up getting a new exponent of negative 1/2. And instead of dividing by negative 1/2, I multiplied by negative 2 over 1. So that's where the negative 2 came from. I don't need my constant of integration because I'm evaluating it from 1 to 5. I'm going to use my fundamental theorem of calculus. I am going to rewrite with my positive exponent, so the negative 2 stays on the top where it's at. I'm going to bring that x to the negative 1/2 down to make them positive. I'm going to plug in my upper limit. I'm going to plug in my lower limit. And remember, x to the 1/2 is the same thing as the square root of x. I'm going to simplify a little bit, and I end up getting negative 2 over rad 5 plus 2. If you were to put this in your calculator, you end up getting a little over 1.1. So what that's saying is that I have this function, x to the negative 3/2, and I'm finding the area underneath the curve of that function from 1 to 5. So if you look down here at the bottom, this is the graph of the function that we're talking about, x to the negative 3/2, and we're finding the area from 1 to 5, and we end up getting that that area is a little bit over 1.1 square units, right? Okay. So then what if I took that same exact problem, but instead of integrating it from 1 to 5, I integrated it from 1 to any number, let's say 1 to b. And so doing that same process, I could find the antiderivative just like I did before. We're evaluating it from 1 to b. And so if I plug in my upper limit and I plug in my lower limit, I end up getting this expression that represents the area underneath the curve from 1 to any number, b, right? And so if I'm looking at the picture, I can find the area underneath this curve from 1 to any number I choose over here. And I can find that area, as long as I know what b is, I can plug it into that expression and figure out what that total area is. But what if I started at 1, but I didn't end? And I wanted to find the area and keep going and going and going and going and going and going and going. And I didn't stop. For example, look at this third one. I took the same exact function, and I want you to find me the area underneath the curve, starting at 1, going to b, but eventually I want you to make that b go all the way to infinity. So I want you to start at 1 and keep going and going and going and find me the area underneath that curve. Let's work it out and see what happens. So just like I did in the previous problems, I'm going to find the antiderivative. So I have the negative 2 over x to the 1/2. I'm evaluating it from 1 to b still, right, over here. And then eventually I'm going to make that b go to infinity. I'm going to use my limit idea and make b go really, 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 really big. Okay? All right, using my fundamental theorem of calculus, I'm going to plug in my upper limit. I'm going to plug in my lower limit. And I end up getting the same expression that I got in the middle problem, but now I want to make b go to infinity. I want b to get really, 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 really big. So think about what would happen if you plugged in a really big number down here at the denominator. If I have negative 2 over 1,000, or negative 2 over 10,000, or negative 2 over 1 million, do you remember what happens with our fraction value when our numerator stays the same but our denominator gets really, 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 really big? Do you remember that that fraction actually gets really, 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 really small? And so eventually it just turns into 0? So then I have now a new problem that says that I really have 0 plus 2. right? As b got really big, this fraction turned into a really small number and eventually it approached 0. So now I have 0 plus 2. And so really I could say that if I were to extend that area underneath this curve and keep going and 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 going, the amount that I end up adding to it is so insignificant that eventually the total area just turns into 2 square units. Pretty cool, huh? You would think that it would just keep adding and adding and adding and adding and get bigger and bigger and bigger. Now, sometimes that does happen, but sometimes the area that we end up adding is so small that it doesn't really add any more to our total area, and we end up getting an actual value, like